Hey, thank you for having us here. Thank you for everyone who supports Ukraine and attending this conference. Any support for Ukraine at this time is a lot valuable. So we do, as Ukrainians, we do appreciate your support. So, greetings. Today, I'd like to talk a little bit about Project Panama. So we're kind of short on time, so let's get to the point. My name is Dennis Makogon. I'm principal member of technical staff and Java advocate at Oracle. You probably seen me at one of the conferences mentioned on on the slides. It's like some kind of a pitching. So let's get to the point. For quite a long time, Java developers been using technology called Java Native Interface, a solution that allowed to bring native code into Java applications. For the first and foremost, the advantage of that such technology is that it allowed to bring solutions that either weren't available in Java ecosystem nor possible to implement in pure Java. Um, but its power and a weakness is that this code is first platform specific. Second, it has a dependency. It has a C compiler and or C++ compiler as a dependency. The purpose of Project Panama is to change the way developers interact with native code from inside of Java applications. In this talk, I'll try to cover both foreign functions and memory APIs and JDK code generating tool JExtract, leaving Vectors API for, let's say, another time. Foreign functions and memory API offers a variety of APIs that attempt to give an answer to the following question: how to invoke a native function of a particular signature by its name. Uh, every of these highlighted words correspond to a particular API class or a group of them. Uh, that is a member of foreign functions in memory APIs. So let's start with the linker. Linker, in terms of a computer science, is an implementation of C application binary interface, which purpose to provide unnecessary capabilities to perform both down calls and up calls from the high level system to lower level system. And the up calls work basically in the opposite way. So the C code can call Java code, and Java code can call C code, which calls the down calls. So invoke, um, yeah. So basically, it is a linker implementation inside Project Panama supports every popular targeting platform: Windows, Linux, macOS, including the most popular and new target platforms like ARM chips or for M1 chips for macOS and for ARM architecture for Linux. While linker answers to a question how to call a function that you have, a simple lookup class is more about how to find a function by providing an interface for searching an address of a native function using its name. At the same time, symbol linker gives you an answer where the function is located. It doesn't give any hint what kind of function that is. So a function descriptors API is the way to describe what kind of a function we'd like to invoke by outlining its signature, return value, positional, and variadic arguments, their types, order, and quantity. It's always good to keep in mind that C code has no idea about Java classes, records, Java types. The only types that it understands are primitive types like float, int, booleans, bytes, char sequences, type def structures, and few others like macros and etc. So these layouts, so value layouts, the memory layouts, value layouts, help a linker to identify what kind of a Java variable uh, of a given size, meaning given byte size, will be mapped to a memory segment that corresponds to the particular Java variable. It's always good to keep in mind that C code has no idea, and yeah, it's it's something like that. So these layouts help to structure the code in order to tell a linker that you want to call this function by saying that it has a return value in the form of Java int, and it accepts a pointer. In Java terms, it's an address. This term is very specific to Project Panama because this is the way to bind C types to Java types, but in a form not of a direct variable, but in the form of the layout or sketch or call it wherever. So basically outline what is the carrier type of a variable that will be passed to a native function through the parameters from Java application. Instead of following the same programming model as with the JNI, foreign function and memory API provide more advanced solution by providing the method handles as an executable object bound to a native symbol using its address, a function and a function descriptor which describes the parameters and return value in their order. At the same the declared function descriptor is that type of a resource that tell to JVM that to tell the JVM what method type given method handle must have in order to comply with the original C function signature. More interesting concept is the up call comparing to the down call because we're talking about Java calling the C code, which was available even even with the JNI. But while the down calls allow you to invoke some native code, up call allow low level system to invoke Java code. At first, it may sound um, like something will be invoking the code from the JVM, but it's actually not. Similarly to down calls, we can form a pointer to a Java method through a method handle and then pass it down to a native function in form pass into a native function as a parameter. But I mean, a parameter, it would be a memory segment that holds a pointer that is understandable by underlying C code and it would be a function pointer, which is a specific type of a pointer in C. And then using that pointer, C can call back if you perform the invocation of a particular function that was bound to that memory segment from inside of a Java application. So the C code that can construct and call Java methods using C function pointer, which is quite interesting because it allows you to build intercommunication between two systems, while the JVM considered to be a high-level system, a meant to be a lower level system. But even with the C application binary interface, it's possible to perform a down calls to a native code by giving to native code a pointer to Java code, and a C code can execute and get some result from the Java code, and then process it further within a down call that came from the JVM. So you see, almost every aspect of writing Java apps that use native code is somewhat bound to a native or an off-heap memory management. So if some of you have worked with the JNI before, you know that there was a need to properly manage memory, and it's not very specific to JNI, but with for any other compiled languages like C or C++, the biggest challenge for a developer not only to write the code, but also manage to clean up that code. And the memory, and this isn't something this isn't linked to Project Panama because it offers a way to deallocate memory segments once they no longer need it, thanks to garbage collector. And a memory session works. Uh, it has an access to all uh, huge chunk of heap memory. So whenever you will allocate a byte like n byte size memory segment, a memory session later on, once it will be on a closed stage, it will go through every bit of allocated memory and then will deallocate it for you, which is way more better than working with the memory on a lower level systems like in C or C++. Um, and which is very cool, by the way. At the same time, developers uh, can use more advanced memory allocation techniques using segment allocator that allows you to allocate memory arenas. Uh, Arena basically is a large memory segment of a fixed size. Often these arena used in a segment per task use cases, by the end of which the only thing that is necessary to do is to reclaim the whole segment in one go instead of doing a per variable reclamation, which is and if you look at segment allocator, it basically allocates the whole segment at once, and this huge piece of memory is what called arena. uh, and this term is actually came from C++, and some protocols that being developed using C++. When you allocate this a particular size of a memory and then uh, partition that for the particular variables within a particular scope of code. And then once those variables are not needed or the task is finished, you don't have to go and deallocate every piece of memory. It is possible to deallocate the whole arena at once. So segment allocator is kind of lower level uh, memory management subsystem, which kind of isn't a replacement to a memory session, but rather a way to manage a big arena at once using the same API methods. So a segment allocator is not a replacement to a memory session if you want to do something more complex. But memory session, it extends segment allocator, but works against all available off-heap memory. So it means that once you start um, a scope a scope that has a memory session where you have a memory session bound to an off-heap memory. From there, you can allocate as long as you have more memory available. But if you work with the segment allocator, things changing dramatically because at the very beginning, you're saying to the JVM, I want to allocate, let's say, 10 byte long memory segment. And then all I wanted to do is uh, partition that memory for each particular variable in that scope, which could be like, let's say, like a byte array of 10 of 10 species size. But if you will try to go beyond that with the segment allocator, you will get an exception saying that you're basically out of memory within the scope. But this isn't a thing for memory session, and memory session meant to be a standard solution like C malloc if you have worked with that. But if you worked with the C code, you definitely should be aware of that. Um, and not only C but C++. So you can directly map segment allocator to a custom allocation function, which still uses malloc in order to uh, cut out some piece of memory, but and then just give it back to a system. But in Java, you have two options: whether you want to go uh, whether you want to go use the higher level APIs, like a memory session, which works in 100% use cases. But if you know that the code you use can work uh, with the segmented memory, uh, with the memory segments allocated through a memory segment. Sorry for repeating repeating the words, but that's what it is. And then you can use a segment allocator which still bound to a memory session. So you can either use a segment allocator to deallocate the same memory segment, or once your application completes this execution, a memory session that is bound to w- to which a segment allocator is bound, it will still deallocate the whole memory being allocated within its scope. Um, so you see, if we're gonna look back at linker, at function descriptors, at symbol lookup, and memory management, all we see that we use Project Panama tries to provide you the same programming experience and programming model that you have got in C or C++, but there is some um, but there is something which makes it totally different in terms of Java. There's one big difference. In Java code, a developer has to do what the C compiler does for the C code, while memory session is a Java kind of malloc, as I already said, and the rest of the code serves an infrastructure purpose that most valuable and important component of the foreign function a memory API is linker, because it acts like a C compiler in terms of compiling invocation path to native uh, native code with a bit of help of a JIT compiler. And let me explain this because it's very important. We all know that variadic arguments and methods uh, in Java, they exist in Java, but the way they work in C, they work differently. In Java, variadic arguments, or varargs as we call them, support. Java has support over varargs. This is the runtime feature handled by the JVM, but it's C, it's a compile time feature. So the variadic functions exist only in code text. At compile time, they turn into a specific version, a specific variant of itself, but the exact argument types, order, quantity. So if you so this example is kind of good because it shows that there is a function called printf. We all know that the first parameter is a char array, which represents basically a formatting string, and then it has a three dots, which basically stands for the variadic arguments. And once you write this function, you don't invoke it with the three dots. You invoke them with a particular set of parameters, and then when you compile that code, a compiler will create a very specific versions. So if you pass, let's say, another char array, an int, it will expand those three dots by adding additional parameter types to the printf, and then it will create two completely different functions that has its own parent that only exists in code text. So that's the responsibility of a developer to create a very specific. So in Java, with the Project Panama, the responsibility of a developer to create a very specialized version of the same variadic function that will fit the exact combination of the variadic arguments, similarly to what C compiler does. So it means that if you want to have a function that has a variadic arguments in C, and then you want to call it from using the down call from Java application, all you have to do is to figure out what kind of a invocation would be. So you need to know what goes after the formatting string for the printf, for instance. And then using the foreign function foreign function and memory APIs, you can design a specific invocation path to a variadic function, but this time in JVM, you defining the exact uh, parameters it will be invoked as using a memory layout to tell what kind of argument, what's the return value, what's the positional arguments, and what are the variadic arguments. But instead of providing, let's say, Java var args, you have to um, you have to provide the explicit definition. So and to make it passable, so it's not like this C application binary downside that you have to do such thing, so you have to write such code in Java, but something that developers have to live with. Therefore, developers are responsible for not the invocations at the very beginning, but for the rest of the components that make the native code execution possible. So as mentioned before, we're talking about an instance of Linka, a symbol lookup, because there are two instances of the lookup, because Linka has its own lookup and JVM has its own lookup mechanism that you probably have used before using the system.load library to load a library. And it basically appends it looks for a library in a specific for using the name or a specific path. So most important thing, the infrastructure code, a linker, a function descriptor, method handles, and symbol lookup must perform, must have the best performance, even though it's a pretty much static code. But and all of these components has to be static. They has to be in terms of C or C++ code, they has to be constant. But in Java, we're talking about static final fields. So the JIT compiler can go and optimize the code as heavy as possible to make the further native code execution cheap for the runtime. If it's not the thing, so if you decide to develop an algorithm that you will go and make it dynamic in terms of what kind of a parameters the order and the types will be passed to the invocation path. In this case, all of your components that represent an infrastructure code for the native code invocation will become dynamic. So it's either a choice between a flexibility, a parameter-based method handle. So as you see in this code, so you basically have to guess what kind of objects are stored in the object array. But the good thing is that infrastructure code is mostly written once and not very often revisited. So a choice between performance is much more appreciated. So if you know exactly how you will invoke a function, it's definitely better to make everything static so the JIT compiler can serve a good job for you by optimizing that code. But if you decide to create a dynamic definition of a method handle of a function descriptor, you have to be aware that that code uh, will become expensive for the execution, and you have to take into consideration that it will be almost the same expensive as the JNI code, which is quite expensive because there's no optimization done by the JIT compiler against that code. Um, so you see, the only thing that may require a developer to change the infrastructure code uh, is that unless uh, so any change to underlying C code in a header file would only make the a developer to change the definition of those functions. But you see that it's not really important for you to keep an eye on all changes. Project Panama and its developers decided to help every developer who works with a native code to create that infrastructure code for you in the most efficient way. So a new and the first standalone GDK generating tool was developed within the Project Panama initiative, which called JExtract. So it actually does what it sounds like. It extracts code, but actually what it does in reality, it takes a C code and a header file for a library, and then it go through that file and then identifies every native symbol, which is a function, a structure, a type def, a macro, a global variable like a constant, and then create a Java version, Java representation for that code for you. So you see, there's a huge difference between the JNI and the JXOR that uses foreign function and memory APIs. It makes you spend more time by writing Java code instead spending time and working with a non-trivial types inside of the C code that was created for you by Java compiler. So JExtract, by saying a standalone tool, it means that JExtract isn't a part of a JDK distribution because the target audience isn't that wide. So whoever needs it will find a way to download the binary or build it from source. And there is a reason for this. Uh, a binary itself is huge. It's almost 200 megabytes. But when you start digging into it, you see that it depends on CLang LLVM uh, for the front end and for the backend LLVM backend in order to read parse a C code and then have an access to the metadata and then read that metadata and then create Java code for you that will represent one-to-one what the header file, the C header file contains. And the very special thing that it's not a single binary. It's not a single executable binary. It's a J-linked runtime. So basically, it's a Java runtime, which has an additional module being added into the JDK and then linked all together by making the distribution package smaller, as well as it has additional compiled pieces of the CLang LLVM or the libclang library to work with the C header files. So it's already available as a distribution. You can find it on the gtkjava.net. And it's also interesting that so what was this all about? Um, sorry. So what the JXR is about? JXR can generate you a Java package that will contain an infrastructure code for native symbols defined in a target C header file. So instead of writing your own linker, initializing your own linker, you having your own symbol lookup, have your function descriptor and method handles. It can generate everything that for you in the most efficient way. So, and the amount of code basically shrinks to limit itself to the invocation. So, and you're no longer responsible for that code. However, you still have to maintain that code. So the purpose of JExtract is to create a Java package that contains all functions. So whatever is a native symbol, it will be available inside of a package, that package. So for let's say as to the IO, it will create whatever functions are stored there. So if you want to call a printf function, all you have to do is start a memory session, bind a Java string into a memory segment, and then pass that as a pointer, because as you know, printf in C accepts a pointer to Java array. That's how it works. So almost everything that JXR does generates for a native symbol are constants, except one thing. Uh, but there's like a very big exception from what the exact thing that JExtract generate for you, and these are variadic functions. Variadic functions are an exempt from the rule because JExtract tries to be a good fella and provide a dynamic parameter-based solution for native variadic functions. It basically what it does it does exactly what I explained before. It will create a customized array collecting variant of a method handle that will try to guess what are the carrier types of parameters used to invoke the native code to reconstruct both a function descriptor and a method handle to match those parameters. So such solution indeed worked as expected. However, it makes the whole infrastructure code dynamic. Therefore, an invocation become expensive, as mentioned before, and expensive almost as the JNI code invocation. Because this solution is based on the fact that that JExtract, the helper that the JExtract create for you, it tried to guess what's inside of an object array passed um, to a native function. But as you know, the array collecting method handle will take whatever parameters you pass to a method handle and then will create a single object array by packing all the parameters into an array. And then what the gextract does for you, it basically goes and flatten that object array by in the order of the parameters defined by the original um, function descriptor. So for instance, for a C, for the C printf, it will place a formatting string in the first place, and then then will place every parameter mentioned in Java var args used to invoke a function just right after a positional arguments. So what it does, it turns Java var args into a flat. It basically flattens that. So and it actually does. So it actually looks like and works exactly as C compiler does, as I explained before. So you're passing the parameters, and then a C compiler forms a new variant, a new typed variant of a function that will be invoked from inside of the compiled binary. So this it works this similarly to it works similarly in Java, but as I mentioned before, this code has to be written by a developer, or in case of the JX, that it can be generated for you. Um, so you having the solution where you write static versions of a variadic functions and having what the JX will generate for you, it's either a choice between agreeing with the less optimized variadic functions, but with the truly dynamic variable arguments, which which is the how the C compiler works, or a heavily optimized JIT compiler constants, but it's in a specialized method handle with this, but with a specialized method handle for each combination of positional and variadic arguments. So from my own experience, I would say that uh, having the code that creates effectively static and final method handles is more efficient, because just imagine how many times you will call that function with the different parameters. So keeping that in mind, you can always create a specific version for that function with a very minimum amount of efforts. But still, you have to maintain that code because it's now written by yourself. And if something change in an underlying library, you will be the one who would need to adjust that code. But as mentioned before, it's not happening that often between minor or micro releases, but in and even but more possible for a major release updates for the underlying C libraries or any third-party C libraries. I'm not talking about only the C standard library and its components like string library, like stdio, like group, like user, and etc. There are a few good cases of using JExtract and foreign function memory APIs in production, like OpenGL for Java, is basically an attempt to bring OpenGL, uh, but instead of working with a JNI, uh, it, a developer who have done this, it basically generated Java code for the OpenGL, which makes it more efficient and way more portable, because in most cases the underlying compiled library is the only subject to change between platforms, but the header file remain almost the same unless we're talking about something very platform specific like Windows APIs or an access to the hardware, which may not be available on a particular target platform. Uh, there is also a Linux GPU built for Onyx runtime for Java. Uh, this one is more interesting because you can compile OpenGL at any target platform, but with the Onyx runtime, you have a matrix where you can figure out for which target platform what kind of a builds it support. And the person who done the Onyx runtime for Java, it built it for the Linux using the GPU. And the most interesting one is JExtract was built using the JExtract. And if you scan this QR code, you will see that a code structure of the JExtract of the one of the JExtract packages corresponds to what JExtract generates for another C libraries. And of course, if we're talking about libclang library, it's a C library, so the JExtract can generate that for it can generate Java classes for that library. So that's why the JExtract first was developed manually, and then once it was ready, the developers basically replaced a handwritten implementation with the auto-generated code, which is kind of cool because JExtract was the first production consumer of its features, which is kind of cool. Um, what about known issues? It all sounds quite interesting and indeed entertaining, but I had to admit that the world isn't that bright and sunny as we expect it to be. Unfortunately, Project Panama can only work with C++ code indirectly through a procedure known as type degrading. For instance, in C++, you can have classes, inline methods, but in C you only have structures, functions that work with the structure through through a pointer. Instead of vectors, you have arrays in C, and of course there are no templates in C, so you have to somehow deal with it. So it's not really a problem of the Project Panama, but rather a libclang that offer not that great interface into C++ code. However, if you are familiar with the LLVM, you know that it consists of a front end and the back end. So think about the idea when LLVM front end translates C++ code into instead of the translate it from instead of a machine code, it would translate it into C code. So from there, it would be able, but that's just an idea that may become a feature based on your request to the GDK team. And also, there are like a couple of more ideas that you can using the LLVM front end that takes a C++ code. It translated to a web assembly, and from there you can use a C++, a WebAssembly decompiler to get a C code from it, and then generate the code from it. There are a few more additional solutions to that, but all of them are a subject for test. And for now, you can only work with the C code. Um, that's kind of the reality. In the meantime, if you're interested in creating C++ API by degrading by creating a library through a C++ API degrading into C API, please go and check a reference project that attempts to bring back OpenCV C++ API into C API that was deprecated, as far as I remember, a couple of years ago. Uh, Also, you could find a few more projects that bring C libraries to Java world, like Tesseract, which use the optical object recognition, and FFmpeg stack, which kind of interesting because it basically can be done without writing a lot of uh, code or even just writing a make file, which is kind of interesting. I definitely recommend you to go and check that. So, anyways, that's it for today. Thank you for listening to me. Thank you for attending this conference. And once again, thank you for supporting Ukraine. It means a lot to us. And it's time for questions. Thank you.
Thank you very much, Denise. And we have questions. So, should native code be synchronized in multi-threaded projects? How properly synchronize it?
So that's a very good and a very that's a very good question. So you see, if you have looked at any other project using JNI, the only place it has a synchronized keyword is that the underlying code is isn't a thread safe. So it really depends whether a function that you call can be called in multiple threads at the same time, and there is no state shared um, between multiple threads. Uh, so it means that if an underlying code is safe for multi-threading, it's definitely possible to call it from the JVM without having it synchronized.
Okay, cool. Thank you very much, Denise. Thank you for your insights into this really complex and important topic. And for today, it's over. Thank you for joining us and see you on the next conferences. Bye bye.
Thank you. Bye bye.